Hello everyone, this is Dr. Ana Angelica Macalalad Josue, and today our lesson will be about the endocrine pancreas and the hormonal regulation of energy metabolism. So this will be the outline of my lecture. First, we're going to have a brief background on the physiologic anatomy of the pancreas. Next, we were going to discuss insulin and its metabolic effect. One of the most important hormones that you will have to study as a medical student. Next, we're going to discuss its alter ego, the glucagon and its function. And lastly, somatostatin, which inhibits both glucagon and insulin secretion. And lastly, we're going to briefly discuss diabetes mellitus, which is the prototype of the disease affected by disorders of energy metabolism. So this is the physiologic anatomy of the endocrine pancreas. So your pancreas is located at the back of your stomach. So your pancreas is composed of your exocrine pancreas and your endocrine pancreas. Your exocrine pancreas is composed of your acinar cells that secrete digestive enzymes, the one that contains your trypsin, your chymotrypsin, your bicarbonate, and together they form your pancreatic juice that is involved in the digestion in your duodenum. But the focus of our lecture today is the endocrine portion of your pancreas, which is your pancreatic islet. Pancreatic islet because it looks like a small island. And here you will find the different cells that secrete the important hormones that is central to hormonal regulation of energy metabolism. So there are about roughly 1 to 2 million islet cells of Langerhans. So if you have diabetes mellitus, your islets of Langerhans will be depleted in number, causing some form of insulin deficiency along the way. So your islets of Langerhans is composed of different kinds of cells, majority of which, 60%, are composed of your beta cells. Your beta cells are located in the central portion of your islets and produce your insulin and your amylin. Next, you have your alpha cells that is located in the periphery of your islet cells. And these cells are responsible for the secretion of your glucagon. Next, you have your delta cells. The delta cells, on the other hand, are very few and intermixed within the entire islet, and it secretes your somatostatin and your gastrin. And lastly, you have your PP cell, or the cell that secretes your pancreatic polypeptide. So these cells do not act independent from one another. They're actually linked by gap junctions that facilitate rapid communication because they're intricately intertwined in energy metabolism that they have to communicate with one another because your glucagon can suppress insulin, while your somatostatin can suppress both your insulin and your glucagon secretion, and so on and so forth. And the portal blood supply of the islets allow blood from the beta cells to bathe the alpha and delta cells, again for rapid cell-to-cell communication. So first, let's discuss insulin and its metabolic effects. So it's important for you to master insulin because the understanding of insulin is important in understanding diabetes. And when you go into the clinics, diabetes is one of the most common, if not the most common metabolic disorder that you will encounter in the clinics. No? It was first isolated from the pancreas in 1922 by Banting and Bess. And these two scientists won the Nobel Peace Prize for its discovery and isolation of insulin. Why? Because during that time, a lot of people were dying from diabetes mellitus. So just as an example, we have Leonard Thompson, a 14-year-old boy who was dying at the time of diabetes. Most likely, this patient was afflicted with type 1 diabetes. Look at that, that boy, that very skin and bone boy that looks like an 8-year-old boy instead of a 14-year-old boy, was already drifting in and out of diabetic coma, and he only weighed 65 pounds. And he was the first human that was given the experimental dose of insulin. The original, the first successful insulin was actually isolated from the pancreas from dogs. Initially, the impure form of the insulin failed, but they were able to isolate it and was able to generate a purer version. And this purer insulin that was injected to Leonard restored his blood glucose level back to normal, and his symptoms began to disappear. And from this, he became this boy. He gained weight, no, probably achieved some growth and development. However, when Leonard was 27 years old, 13 years after his insulin injection, after his first insulin injection, unfortunately, he died of pneumonia, which was also thought to be a complication of diabetes. Lucky for our patients today, we have lots of insulins that are already available, synthetic insulins, both human and analog insulins, or newer insulins that are available for our patients with diabetes. And this has significantly improved the quality and the quantity of years that our patients with diabetes have, and have remarkably reduced the incidence or the prevalence of diabetic complications. So insulin is a hormone associated with energy abundance. When you hear insulin, insulin is an anabolic hormone, no? It serves to store energy. So if there is abundance of food that provides energy, it promotes secretion of insulin, and secretion now facilitates its storage of energy. If it's carbohydrates, it gets stored into glycogen and eventually into fats. If it's protein, there is an increased amino acid uptake by cells and inhibits protein breakdown. So it's an anabolic hormone. So what happens? So how is insulin secreted? So again, the cells it produce is your beta cell, and it's initially synthesized as a pre-pro-insulin. So this, and then your pre-pro-insulin is cleaved, no? Cleaved to form your pro-insulin, and eventually it undergoes translational modification inside your cells. And this C-peptide or your C chain is cleaved from your pre-insulin, and when the C-peptide is cleaved, you are able to release your insulin. So your insulin is composed of two chains, your alpha and beta chains, connected by two disulfide bridges. Okay, so since they are form an the C-peptide and the insulin form part of your original pro-insulin, they are secreted in the beta cells in equimolar amounts. But your insulin has a very short half-life. If injected through IV, its duration of action is only 10 to 15 minutes, and it is rapidly degraded by your enzyme insulinase in the liver, which is found in the liver, also excreted in the kidneys, and degraded also in your muscles. But your C-peptide has a longer half-life, and since it has a longer half-life, longer than your insulin, it enables us to measure it. So if you're able to measure C-peptide, it's an indirect measure of how much is your endogenous insulin production. So your C-peptide, sometimes we request this to determine how much insulin reserve the patient still has, or if the patient is already insulin deficient, or the patient has hyperinsulinemia. Okay. So what happens? How does insulin act on your cells? So when your insulin attaches to the target cell receptors, no, it activates the target cell receptors and causes intracellular effects. So it has been thought that insulin sort of acts like a key to the cells in order for glucose to get inside the cell. No? So if there's no insulin, your glucose cannot enter your cells. So it acts like a key so that the cell will be able to take in glucose and utilize it for energy production, or it can be converted into glycogen, it can be converted to triglycerides, and be used for energy production, for ATP production. So without insulin, the glucose cannot enter through its glucose transporter. Okay, so if there is starvation, you will have an increase in insulin receptor so that more glucose will enter the starving cells. But if in a patient that is obese, no, there's energy abundance, you don't need a lot of uptake of glucose, so the insulin receptors are down regulated. Okay, so when insulin attaches to its receptor is a tyrosine kinase based receptors. It results in numerous intracellular processes that, well, for one, facilitates glucose transport intracellularly, and aside from that, stimulates anabolic processes such as protein synthesis, fat synthesis, glycogen synthesis, growth, and gene expression. So it's about building. That's why it's called an anabolic hormone. So what happens when insulin is able to stimulate your body cells? So 80% of the body cells markedly increase their uptake of glucose, no? Because your insulin, as I mentioned earlier, acts like a key. So glucose can enter. So glucose can enter your muscles, your adipose tissues within seconds. There is an exception. The exception is the neurons in the brain. So their brain cells does not need insulin in order to utilize glucose, because your brain is an obligate user of your glucose. Your insulin also results in translocation of multiple intracellular vesicles to the cell membranes. Aside from uptake of glucose, it also increases permeability to the amino acids so that there will be protein building blocks for protein synthesis. It also increases uptake of potassium into the cells. That's why in patients with hyperkalemia, meaning markedly elevated serum potassium, we usually give IV insulin in order to facilitate entry of potassium from the extracellular fluid to the intercellular to decrease the serum potassium. Phosphorus also increases its entry into the cell. So your insulin also changes the activity levels of many more intracellular metabolic enzymes within 10 to 15 minutes. And it also changes rates of translations of mRNAs. Why? Because you want to activate the translation of your DNA to mRNA so that it will now be able to be translated into proteins. And what proteins am I talking about? Your enzymes. And the enzymes will be the one powering the different metabolic processes inside the cells. So insulin remolds much of the cellular enzymatic machinery to achieve some of its metabolic effects. So for example, remember your insulin is important in glycogenesis. So the insulin will upregulate the translation of your DNA transcribing your enzymes for gluconeogenesis. So there will be more enzymes that will facilitate glycogenesis. Okay? So what is the effect on insulin on carbohydrate metabolism in the muscle? Resting muscle uses free fatty acid as its source of energy. But after a few hours, after a meal, or after an exercise, the insulin promotes muscle glucose uptake and metabolism by about 15 times because your muscle cells use glucose preferentially over fatty acids after a meal or during exercise. No? So during exercise, you need glucose. That's why before a marathon, no, or before any sports activity, most athletes have to load on glucose-containing food in order to power their muscles because it's the preferential fuel of your muscles during exercise. Your glucose is also stored in the muscle as glycogen, no? Especially when glucose is in abundance, no? And there's no exercise. So that the glycogen will be a ready source of energy anytime you need glucose energy to power like sudden muscle activity, no? So for example, you decide to do a sprint, no? Your muscle will break down glycogen in order to provide readily available glucose to power your sprint. How about in the liver? How about the effect of insulin on carbohydrate metabolism in the liver? So your insulin promotes liver uptake, storage in the form of glycogen, and use of glucose. So in between meals, your glycogen, so when you're not eating, your glycogen is split back into glucose so that your glucose can power your cells. No? And it's released in the liver to keep the blood glucose concentration from falling too low. So for example, when you sleep, you don't eat. No? You don't eat, how do you think you'll be able to survive the next day without glucose? No? It's because of your hepatic glucose production. So your liver is able to produce glucose in order to maintain your body's glucose levels so that you will not die of comatose, no? So, and the source of that will be the glycogen stored in your liver. So almost 100 grams of stored glycogen is located in your entire liver. So some patients would wonder why even if they don't eat anything during dinner, they had an overnight fast. Patients with diabetes will check their blood sugar and they will see that their blood sugar is still high. It's not because they did not eat, but because their liver is able to produce glucose from glycogen. And if you have insulin resistance, like in diabetes, the hepatic glucose production is promoted. So your insulin inhibits gluconeogenesis in the liver, but instead promotes conversion of excess glucose into fatty acids. No, it's also, so the excess glucose, if it's not converted into glycogen, it's converted into fatty acids and eventually converted into triglycerides. That's why patients with elevated triglycerides, usually they're very heavy carbohydrate eater. So when I see my patient's lipid profile and I see their triglycerides level are very high and I ask them, are you eating a lot of rice, pasta, bread, noodles? And they say, yes, doctor, I eat a lot of carbohydrates. So because I can see right away in their lipid profile that they have very high triglycerides, and it's because of the increased conversion of the excess glucose into fatty acids, and the fatty acids is now converted into your triglycerides. So lack of effect of insulin on glucose uptake and usage by the brain is because glucose can readily enter brain cells without the need for help from insulin because the brain cells are readily permeable to glucose even without insulin. Okay? So again, your brain doesn't need insulin in order to utilize glucose. How about fats? How about the effect of insulin on fat metabolism? So insulin doesn't only have an effect on glucose metabolism, on sugar. So it also affects fat metabolism. So as I mentioned before, insulin is an anabolic enzyme, anabolic hormone. Therefore, your insulin promotes fat synthesis and storage, no? So it spares fat because it shifts your metabolism towards use of glucose. No, that's why patients who are insulin resistant, usually they're fat, or patients, one of the side effects of insulin injections, high dose insulin injection, is weight gain. No, they gain a lot of fats because that's one of the effects of insulin on fat. So excess glucose is converted into substrates for fatty acids. So as I mentioned earlier, your glucose is converted into free fatty acids in the liver, and the free fatty acids are your building blocks of your triglycerides, and your triglycerides is a form of storage fat. So that's one of the ways by which insulin stores energy, aside from glycogen. So your insulin activates lipoprotein lipase in the capillary wall. So what happens? So what does your lipoprotein lipase do? So your lipoprotein lipase promotes deposition of your triglycerides in your capillaries. Therefore, on the other hand, your insulin inhibits the action of your hormone-sensitive lipase. So it stimulates lipoprotein lipase, but inhibits hormone-sensitive lipase. So what does hormone-sensitive lipase do? Your hormone-sensitive lipase is responsible for the hydrolysis, or the breakdown of your triglycerides. So insulin inhibits the breakdown of your triglycerides because it wants to promote storage of fat. So what happens if you have insulin deficiency? If you have insulin deficiency, it increases use of fat for energy. So remember that Leonard, the boy with type 1 diabetes, who was very, very insulin deficient, he almost has no fat at all in his body because most of the fats are used up for energy production. So if you are insulin deficient, people with diabetes that have very poor glucose control are very insulin deficient. They usually lose a lot of weight. No? So that's one of the symptoms of diabetes. And this is because of lipolysis, or breakdown of storage fats, and release of free fatty acids. And this is facilitated by your hormone-sensitive lipase. So remember, lipoprotein lipase, no? It's the deposition, it's the storage of triglycerides in your capillary walls, while your hormone-sensitive lipase is the breakdown of your triglycerides. So your free fatty acids will now be converted into gluconeogenic precursors in order to be used for production of glucose. And the glucose will be the one used for energy production. When there's also insulin deficiency, there is increases in plasma cholesterol and phospholipid concentrations, and occasionally plasma lipoproteins. And insulin deficiency also promotes the development of atherosclerosis in people with severe diabetes. So atherosclerosis increases the risk of stroke and MI, or heart attack, by about 4 times in people with diabetes. No? Excess usage of fats during insulin deficiency causes ketosis and acidosis. So in severe cases of insulin deficiency, there is, and the patient becomes decompensated, patients can develop what we call diabetic ketoacidosis, no? Where you will have metabolic acidosis and markedly elevated blood sugar because of severe insulin deficiency. How about the effect of insulin on protein metabolism and growth? So just like your fat and your glucose, insulin also promotes protein synthesis and storage. It increases the transport of the many amino acids into the cells so that these amino acids can be used as building blocks for protein synthesis. It also increases translation of mRNAs, thus forming new proteins, especially your enzymes. It inhibits catabolism of proteins and depresses the rate of gluconeogenesis because why? They want to conserve amino acid substances. So the substrates, remember in biochemistry, we use amino acids as gluconeogenic precursors. So in order to prevent breakdown of protein into amino acids, your insulin depresses the rate of gluconeogenesis. So insulin deficiency causes protein depletion and increase in plasma amino acid. So it's the opposite. Other insulin effects, insulin decreases blood potassium concentration because remember your insulin increases uptake of potassium to enter the cells. And your insulin and growth hormone act together to promote growth and development. So patients with type 1 diabetes, no, children who have type 1 diabetes who have very poor control, sometimes they have some form of growth retardation as well. So to summarize all of the anabolic effects of insulin, no? So it promotes muscle glucose uptake and metabolism, liver uptake, storage, in the liver uptake of glucose and storage in the form of glycogen and utilization of glucose, conversion of excess glucose into fatty acids, fat synthesis and storage, protein synthesis and storage, and on the other hand, it inhibits gluconeogenesis in the liver in order to conserve amino acids for protein building. And lastly, it inhibits fat utilization. So how do we regulate insulin secretion? So first, the major factor that regulates insulin secretion is your blood glucose concentration. So as you can see from this graph shows not in the x-axis, you have your plasma glucose concentration. And on the y-axis is your insulin secretion. As you increase your glucose concentration, your insulin secretion also increases so that it will facilitate the uptake of glucose into your cells. No? So insulin secretion during a glucose stimulus is very dramatic, both in its rapidity and in the high level of secretion that is achieved. Although, of course, there is a limit. So, for example, if your blood sugar is already 600, no, your insulin can only do so much, no? So, it's important that you keep your levels within acceptable limits so that you will not push your insulin secretion into hyperinsulinemia. So, within minutes, no, there is a first phase of secretion of plasma insulin with the sudden increase in blood glucose, and then after a few minutes there will be a second phase. This one, it's delayed but higher and continuing increase in concentration after 15 to 20 minutes. So the first phase, no, this part is caused by immediate dumping of preformed insulin from the beta cells of the islets. And then the additional increase is because of additional release of preformed insulin and from activation of the enzyme system that facilitates the synthesis of new insulin. So this part from preformed insulin, this part from new desynthesized insulin. So what are the things that increase insulin secretion? All of these factors. And what are the factors that decrease insulin secretion? So if there's decreased blood glucose, your blood glucose is also already very low, you don't want to promote further reduction of blood glucose. So you want to suppress insulin secretion. Fasting, no? Again, somatostatin, alpha adrenergic activity, and leptin. So amino acids strongly potentiate the glucose stimulus for insulin secretion. So there's another concept called the incretin effect, no? That is also important in secretion of insulin. So your incretins, your GLP-1 and your GIP, these are substances that is released in your gut, no, after a person eats a meal. So when you eat a meal, this is released in your gut, and your GLP-1 and your GIP-1 will act on your beta cell to increase the rate of insulin release from the pancreatic beta cell in response to the increase in plasma glucose from your meal. So again, so when you eat, what will happen? Your GLP-1 and your GIP-1 producing cells in the gut will release GLP-1 and GIP, and this will act on your beta cell to increase insulin release, no, from your islet cells. And at the same time, it not only increases insulin release, but also inhibits glucagon secretion. So it stimulates two things: insulin release and inhibits glucagon secretion. So they're opposite. So there are certain therapies for diabetes that takes advantage of this incretin effect. So some drugs promote GLP-1 and or there are GLP-1 agonists or drugs that promotes the secretion of insulin to lower down blood glucose of your patients with diabetes and suppress glucagon, because your glucagon effect is to increase the patient's blood sugar. So what are the other hormones that affect insulin secretion? Your glucagon, your growth hormone, your cortisol, and to a lesser extent, progesterone and estrogen increase insulin secretion. So patients with, let's say, acromegaly is growth hormone excess. Cushing syndrome is a cortisol excess. These patients also have secondary diabetes. So this is because large quantities can occasionally lead to exhaustion of the beta cells, no? Increasing the risk for the development of secondary diabetes. So as I mentioned, it's your acromegaly and your Cushing syndrome. So parasympathetic stimulation, on the other hand, increases insulin. Remember, parasympathetic is rest and digest. So when you eat, it promotes insulin secretion. If it's sympathetic, it promotes glucagon secretion, because in sympathetic, remember, it's fight or flight. You want glucose in order to power yourself from running away from the lion. So you need glucagon. Epinephrine is another hormone released from the adrenal medulla, and it is important in increasing plasma glucose concentration during periods of stress. No? It has a potent effect on causing glycogenolysis in the liver. So when you're stressed, your body needs energy. No? So when your body needs energy, it needs glucose. It gets glucose by breaking down glycogen from the liver, so that you will have large quantities of glucose into the blood within minutes. The downside of this is that in some stress states, you will have what we call stress-induced hyperglycemia. So let's say you have an infection or you have a very stressful life situation that can aggravate your glucose levels, markedly increase it, and cause stress-induced hyperglycemia with or without the patient having diabetes. Your epinephrine also has direct lipolytic effect on the adipose cells, activates adipose tissue, hormone-sensitive lipase. So your hormone-sensitive lipase, remember, it functions to break down your triglycerides into free fatty acids for energy. So how is insulin secreted from your beta cell? So let's imagine this is your beta cell. No? So when there is an increase in glucose, the glucose enters your pancreatic beta cell through your glucose 2 transporter. So remember that the glucose 2 transporter is frequently asked during exam. So your glucose 2 transporter facilitates the entry of glucose into your pancreatic beta cell, and your glucose is converted by your glucokinase into your glucose 6-phosphate. And your glucose 6-phosphate is eventually oxidized, and this results in production of ATP. Remember in your biochem. So when there's an increase in ATP, it closes. This results in the closure of your ATP potassium channel. And when this is closed, it increases potassium level inside the pancreas. And when there's an increase in potassium level inside the pancreas, this causes depolarization. And if there's depolarization, it opens up the calcium channel. And when your calcium channel is open, it facilitates entry of your calcium. And your calcium now, increasing intracellular calcium, facilitates the release of your insulin from your pancreatic beta cell. And the release of your pancreatic beta cell is inhibited by your somatostatin and your norepinephrine. So it's been said that your glucokinase is the rate-limiting steps for glucose metabolism in the beta cell. So it's also has been termed as the major mechanism for glucose sensing. So if you have a defective glucokinase, your beta cell will not be able to sense the level of glucose in your blood. So what happens in your blood, when you, in the well-fed state? Say after you eat like a cheeseburger. After you eat a cheeseburger, the glucose from your food is transported into your portal vein and goes into your liver, And it is also sensed by your pancreas, and your pancreas will now release insulin. And the insulin will now facilitate the conversion of your glucose into glycogen in the liver, or facilitate conversion of glucose to pyruvate, and the pyruvate will now be the one converted to fat, so that your glucose will be stored as glycogen or fat. Now, some of the glucose, if insulin acts on your muscle, it gets stored in the muscle as glycogen, or it gets used up for muscle activities. The fat is also stored in your adipose tissue, although in the brain, the glucose is readily transported inside your neurons. So this is what happens after you eat. Now we go to the counter-regulatory hormone of your insulin, which is your glucagon. So your glucagon is a hormone secreted by the alpha cells in your pancreatic islets. And this is secreted when your blood glucose concentration falls. It's diametrically opposed to those of insulin. So it's almost always opposite effect of insulin. So if insulin is anabolic, glucagon is catabolic. If insulin decreases blood glucose levels, your glucagon increases blood glucose level. If your insulin inhibits gluconeogenesis, your glucagon promotes gluconeogenesis. It's almost always opposite, okay? So remember, your glucagon is a hyperglycemic hormone. Its goal is to increase blood sugar levels. Insulin is the opposite. Your insulin, remember, it's given to patients with diabetes with high blood glucose in order to lower down the blood glucose levels, in order for the blood glucose to enter the cells. So what are the effects of glucagon on glucose metabolism? So it Its effect is breakdown of liver glycogen or glycogenolysis and increased gluconeogenesis in the liver. So the net effect of glycogenolysis and gluconeogenesis is to increase blood glucose levels in order to enhance the availability of glucose to the other organs of the body. What are the other effects? Your glucagon activates adipose cell lipase, making quantities of fatty acids available, and your fatty acids will eventually be used as gluconeogenic precursor in order to promote gluconeogenesis. Your glucose, in contrast to your insulin, inhibits the storage of triglycerides in the liver. Your glucagon also enhances the heart, increases blood flow in some tissues, enhances bile secretion, and inhibits gastric acid secretion. So how do we regulate? Just like insulin, it's also blood glucose. That is the most important stimulus for the secretion of your glucagon. So for example, remember this graph, in the x-axis, you have your blood glucose. In the y-axis, you have your plasma glucagon. So if your blood sugar is very low, your glucagon is increased. Why? In order to raise blood glucose level. But if your blood glucose is within the normal range, usually the secretion of glucagon is just low. Okay? So what are the factors that increase glucagon secretion? So of course, a low blood glucose will trigger the release of glucagon in order to raise the blood glucose back to normal. Any increase in amino acids can also increase glucagon secretion and all these other hormones also. What are the factors that decrease secretion? So if you have already elevated blood glucose, you will suppress glucagon production because you don't need any more glucose. You already have more than enough. Insulin also suppresses glucagon secretion, somatostatin. Okay? Other things that stimulate secretion of your glucagon, exercise, increase blood amino acids. After a high protein meal, you can this also secretes glucagon. So this is one of the effects that are similar for both glucagon and insulin. So what happens if you're in the fasting state after you eat or in between meals? Now, in between meals or in the fasting state, the enzyme that is more predominant is your glucagon. So if you're not eating, your blood sugar will start going down, and the decrease in blood glucose level will trigger the pancreas to secrete more glucagon. No? And the glucagon will now stimulate gluconeogenesis, free fatty acid glycogenolysis here, in order to increase glucose level. And you will need to utilize gluconeogenic precursors, such as your lactate, in order to facilitate gluconeogenesis. So just to tie them up both together, so again, when you eat, let's say you eat a Big Mac meal, what will happen? It will trigger the release of insulin from your pancreas. The insulin will now serve as a key in order to let the glucose enter the cells through your glucose transporter 4 or your GLUT4 transporter, so that your blood glucose level will start cooling down. Your insulin also promotes glucose uptake in the muscle, in the fats, and in the liver as well. And in the liver, it will promote glycogenesis and suppress gluconeogenesis. So essentially promotes glucose storage. And when glucose is stored inside the cells, your blood glucose levels will go back to normal. What happens if you go to sleep or you're not eating? When you go to sleep, you're no longer eating, your blood glucose level starts to go down, and this is sensed by the pancreas, and this results in the secretion of your glucagon. And in order to raise your blood glucose levels, Your glucagon will stimulate the breakdown of your glycogen to glucose and the formation of new glucose through gluconeogenesis. And this will raise the blood glucose back to normal levels so that your blood glucose levels is just maintained even if you are sleeping. So lastly, we're going to go into somatostatin. So your somatostatin is produced from the cells of the islets of Langerhans, and it has a very short half-life. And what is its function? Just like in the other endocrine glands, like your pituitary, in your gut, your somatostatin inhibits insulin and glucagon secretion. So what are the factors that stimulate somatostatin secretion from your delta cell? Any increase in blood glucose, increase in amino acid, increase in free fatty acids, increased concentrations of several of the GI hormones released in response to blood, because the somatostatin acts to countercheck the secretion of insulin. Remember, when there's an increased blood glucose, your insulin goes up. If there's no somatostatin, some of the insulin will be overproduced, and this can result in hypoglycemia. And the somatostatin function is to keep things in check. No? So most of its effect is really inhibitory. As I mentioned, it decreases secretion of both insulin and glucagon. This prevents rapid exhaustion of the food. So for example, the insulin is in overdrive. So all of the food will be stored in the cells, making it available. And if glucose is stored inside the cells, then your blood glucose levels will not be maintained. So if we prevent the rapid exhaustion of food, it makes it more available over a longer period of time. So your somatostatin also decreases motility of the stomach, decrease secretion and absorption in the GIP. So the net effect will be to extend the period over which the food nutrients are assimilated into the blood. So if there's decreased motility, there will be more time for the food to be absorbed in the stomach, the duodenum, and then there will be slow absorption of the nutrients in the gut, so that the food will be maximized, that the assimilation of nutrients from the food will be maximized. Now we go to the last part of our lecture, which is diabetes mellitus. This is just like a brief introduction of what diabetes mellitus is. I'm sure most of you will have like a relative who have diabetes mellitus, or have know someone who have diabetes mellitus. And diabetes mellitus is a condition where there is impaired carbohydrate, fat, and protein metabolism caused by either lack of insulin secretion and or decreased sensitivity of the tissues to the insulin. So in number 2, usually this is type 1, lack of insulin secretion. There's no insulin, or there's insulin deficiency, or not enough insulin. In number 2, you have insulin, but the insulin is not working very well on your cells. So therefore, the insulin is not very effective in achieving its target on the cells. So that's what you call insulin resistance. So the net effect is, if there's insulin resistance or insulin deficiency, it prevents the efficient uptake and utilization of glucose by most cells of the body, except in the brain. So remember, your insulin acts as a key so that the glucose will enter the cells. If you don't have that key, the glucose will not be able to enter. So if it will not be able to enter the cells, it will just remain in the blood. So these patients will have markedly elevated blood glucose levels. 2 types, you have your type 1, usually it's because of insulin deficiency. Usually, the beta cells are unable to produce insulin. In type 2, usually it starts first with insulin resistance. So you have insulin. Here in this diagram, you have insulin, the purple diamond, but even if it tries to act on the target cell, it's not working very well. So your glucose, this green one, cannot enter the cell. In type 1, you don't have any insulin. So your glucose is also unable to enter the cell, so it just remains in the blood. So type 1 is insulin deficiency. Usually it's an autoimmune disorder where your beta cells are destroyed. If your beta cells are destroyed, you will not be able to produce insulin. Okay? In type 2 diabetes, you have insulin, but it's not able to act on the cells. Eventually, when your beta cells are exhausted from trying to produce a lot of insulin in order to lower down your blood glucose, they also die, and eventually these patients would have some form of insulin deficiency as well. And when the patient with chronic type 2 diabetes mellitus develops insulin deficiency, they would need insulin injections. Okay? These are just nice to know. So this is just a summary of everything. Okay, you just go through this, memorize, no, not really memorize, but understand this. No, this is the summary that we've talked about for the last hour. Okay, so if there's high blood sugar, beta cells will be activated in order to produce insulin, in order to store energy, anabolic, building, okay, so that your blood glucose will go down. So when your blood glucose goes very, when your blood glucose is very low, declining blood glucose levels, your alpha cells from the pancreas will secrete glucagon, and the end result of the glucagon is to break down sources of energy such as glycogen, fats, and even protein in order to produce glucose so that your blood glucose level will go up back to homeostatic levels. So this is the summary. I'll just read this through. In the liver is an important blood glucose buffer system. Remember, that's the organ that does the glycogenesis, glycogenolysis, gluconeogenesis, hepatic glucose production. So it's an important blood glucose buffer system. And both insulin and glucagon function as important feedback control systems for maintaining a normal blood glucose concentration. In severe hypoglycemia, this stimulates the sympathetic nervous system in order to activate the secretion of your epinephrine. And then remember, your epinephrine helps break down fat in order for fat to be utilized as a source of energy. And over a period of hours and days, your growth hormone and your cortisol levels will also help, no? Help increase blood glucose levels in patients who have prolonged hypoglycemia. Now, and your growth hormone and your cortisol will promote fat utilization, and the breakdown of fat will produce free fatty acids, and the free fatty acids will now be used as eventually as gluconeogenic precursor in order to produce glucose, in order to raise blood sugar levels in order to resolve the hypoglycemia. So together we can halt the rise and beat diabetes. So I hope when you become primary care providers or you become subspecialists, you will not forget diabetes, because diabetes was one of the most important comorbidities that really reduces the quality and quantity of life of our patients. But if it's well controlled, well treated, patients with diabetes will live long and fruitful lives. Okay, so together let's beat diabetes. Thank you for listening.